Hello everyone, welcome to class 21 of CS1. I'm Pratap from Smears Education Solutions. I'll discuss a very important topic today, the central limit theorem, which is the most fundamental in all of statistics. Even this is the cornerstone of modern statistics. We need 4 classes for this. This is the first class of central limit theorem. Let's get started. We have a city and we need to estimate the average height. We have picked only the guys who are age 30. Suppose we have 1 crore people. Now, if we want to know the average height of these people, we have to go to each and every one. We need to take their heights. We need to measure their heights. Then we have to find the mean. It's a very difficult task. Also, in most of the cases, we'll not be able to do that because when we start from one end, by the time we reach this end, some of the people they will leave the city and some more people they will come. Also, if you are interested in age 30, if it takes more than 1 year, then the people they will turn 31 after 1 year. So it's almost impossible to go to reach each and every one and then find their heights and then find their mean height. Finding the mean height mathematically, calculating the mean height for all is very tough here, very difficult. In many cases, it's not possible. So we'll try to estimate mu. There is a difference between estimation and calculation. When you say calculate, this is a mathematical quantity. You need to find everything and then you have to calculate. Because we'll not be doing for all, we say this is estimation. So we'll try to estimate mu from sample. We have taken a sample here and then we found the sample mean. Sample mean says something about the population, but not everything about the population. Because if the sample is representative of population and fortunately you got a sample which is unbiased and whatever way the population is, the sample is also in the similar way, then we're fortunate enough to predict, to say something about the population mean. When I say population mean, that is in totality. We are taking all. When we say sample mean, we are finding mean of the sample here. 160 centimeter, 162, then 158, and then 160. Then we can find here easily x bar, and that is 160. So basing on x bar, we will not be able to estimate properly mu because this is only one sample. We have to take many samples and we have to find the means. We'll check what is the link between the sample mean, this is sample mean, and this is population mean. We know this, we have no idea about this. This is we have calculated here, this is calculation, here this is estimation. So here instead of taking one sample, we'll take 4 samples. We'll measure their heights and find the mean here. For the second sample, we'll measure their heights, we'll find the mean. For the third sample, we'll measure their heights and find the mean. And then for the fourth sample, we'll measure their heights and find their mean. That way, we'll take so many samples. Instead of one sample mean, now we have so many sample means. If you have so many sample means, then only you will be able to draw a graph and you see how many sample means are close to mu, how many are far away from mu. Central limit theorem says mainly 3 things. One of them is mean of these mu's is equal to mu. So if you have so many means here, sample means here, you have calculated already, you take the means and that will be the estimate of mu. You can write mu cap is mean up all these means. Suppose you have taken 10,000 times. However, I will not be able to prove that here because I don't know the data. I don't know this one. I will give you a simple example here and I will show you and I will prove it in today's class. Let's proceed further. I've considered a very simple example, rolling a die. This is the most fundamental example. And then I rolled it 5 times. You can also do it. And whatever I got, I have just written here. I got 3, 6, 2, 6, 2. I found the sample mean. I got one sample mean 4. And then I rolled second time. This is the second sample. 5 times I rolled. And then I found the outcomes like this 1, 6, 4, 2, 2. Then I found the sample mean. So here I got sample mean 4. Here I got sample mean 3. Now mu is 3.5. 4 is close to 3.5, though it's not 3.5. 3 is close to 3.5. It's not 3.5. So we have two sample means which are close to 3.5. If you take the mean of sample means 4 plus 3 by 2, that is 3.5. However, this is very simple and maybe by chance I got this way. You have to take thousands of samples. I can take so many samples here and find the sample means manually. It will take a lot of time. So I took the help of coding using Python programming. I found 50. I found the mean of 50 numbers 4 times. So one die is rolled 50 times here for the first time. The same die is rolled 50 times for the second time. And then I found the mean. I rolled it for the third time. Then I found the mean. Fourth time, 50 times. Then I found the mean. When I say n is 50, I rolled 50 times. But 4 times I've done here. That means 50 here, 50 here, 50 here, and 50 here. And I found the sample means. Sample means are these. If you find the mean of sample means, that should be close to mu. However, I've taken only 4. I can take thousands here. So we need the help of programming. I've considered Python programming to find the mean of means. If you're not from Python background, no worries. You can use R programming or any programming language you know. So this is very simple. Randint, I used 1 to 750. This will be excluded. So you get all random numbers from 1 to 6. N minus 1 is the formula. I wanted to get 50 numbers. If you roll a dice 50 times, you get those 50 numbers. Let me run it here. So these are the 50 numbers I got. 2, 6, 5, 1, 2, that way. If you want, you can roll a die, you can get all these 50 numbers. They are one and the same. And what is X bar here? 3.48. 3.48 is X bar. So my sample mean is 3.48. I showed already in my slide 3.48, the first one. So you can roll it 50 times if you have time, or you can use coding. It's only 3 to 4 line of coding. Now come here, 100 times. 100 times I have to do this task. See, this task, I got 3.48 here. I've taken once. Now, if you do it here, I used a for loop. So 100 times will do the same task. So how many X bars are there? You will get 1 to 6. And then you will get the mean also because I've written mean here. 100. 100 means you will get 1 mean we got here. You will get 100 means here. Let me run this one. See, these are the means 3.48, 3.08, 3.2, 3.52, 3.42. If you check the means, they are close to 3.5. Remember, in this case, we know our population mean, and that is how I can prove it. I can prove it that the mean of means is 3.5. We'll do that now. So these are the means. So see how many numbers are close to 3.5. How many are far away from 3.5? 3.5 is the population mean we know already. Just assume that you have no idea about the population mean 3.5. See the sample means. The sample means are very close to 3.5. Even I have not seen 4 point something. Yeah, we got a number 2.88. It's the extreme one. You will get some extremes as well. That is the third thing central limit theorem says. The distribution is normal. We'll go to that. These are the 100 numbers. Okay. And then we'll draw the graph also. Now here, the mean of the samples you need to print. Now these are the means. We'll find the mean of means. See, the mean of means is 3.46. I've taken 100 numbers and I got mean of means. And I want to see the graph. I got this way. It's a bit biased. 3.5 is the population mean. So we expected half to the left, half to the right. You see, we're more to the right. That means you must have got a number something like this, 3.4612. I've taken 100 x bars here, 100 means, and I found the mean of mean. These are the means, x bars. Again, I'm repeating, this is very, very important for you. When I say 3.48, this is the mean of the outcomes, 50 outcomes. This is the mean of 50 outcomes. A die is rolled 50 times. And we have this mean of the 50 outcomes. This is the mean of second 50 outcomes. This is the mean of third 50 outcomes, that way. And we have to find the mean of all these means. That should be 3.5. We didn't get here. We reached up to 3.46. We want to reach 3.5. Let's change n here. We'll make it a bigger. You take 1000, run it. 1000 numbers now. Now do this one. Yeah, 3.499. We reached up to here. And then let me run this one as well. This is a bit better. This looks like normal. This is the distribution of x bar. That means more x bars are there around the center between 3.5 to 3.6. Very less means are to the left extreme and very less means are to the right extreme. So it looks like a normal distribution. And this is the distribution of x bar. That means so many numbers are there around 3.5, between 3.5 to 3.6. Now let me increase it to 5,000 or 50,000. Then we'll do this. Mean of means. Now this is 3.50. We are interested in 3.5. This is very close. We'll not worry about these numbers. Awesome. Now see the graph. I have to run it once again. See the graph. Graph also looks like this. So we got 3.5. We wanted to estimate the population mean and we estimated here exact 3.5. 3.50 up to 2 decimal places, it's correct. Two tasks here. We started with the dice and we knew the population mean already, but we suppose that this is not known and we wanted to reach to 3.5. and with the help of coding, we reached to 3.5. So how we reached to 3.5? We've taken lot of samples and we found sample means, and we find the mean of sample means using coding. The task was very easy. Now, going further, this is central limit theorem. If n is large, you remember I consider n 5000 to reach to the population mean. If n is very large, x bar will follow normal distribution with mean mu. That means if you find the mean of x bars, I'm not writing summation x by n here. Remember, x bar is considered a random variable here. A random variable can only follow a distribution. How x bar is a random variable? Because we are considering so many samples. We have different x bars. We have a range of x bars now. We are taking repeated sample. So mean of this sample should be equal to mu. Now if you see this diagram, more x bars are here. Suppose I've taken 5000. Maybe you have 2000. They're very close to mu. These x bars are close to mu, and there are less numbers like 100 or 50. They're far away from, they're far away from mu. The extremes are low, and most of the data are concentrated around mean. When I say data here, x bar, we are talking about x bar. The distribution of x bar is normal. That means it will satisfy the property of a normal distribution. Most of the data, around 68% of data will be between mu minus sigma to mu plus sigma. So most of the data you will get around here. Most of the x bars are here. If you calculate the number of x bars, I've written 2000 here. If you draw a line here, you may get 1000 again. Here you might get 1000. So the x bars are close to mu. X bars are close to mu, most of the x bars, and very less x bars, they are far away from mu. That's how x bar follows normal distribution. Their mean is mu. Now, if you want to know the standard deviation, suppose these are the x bars, first sample mean, second sample mean, third sample mean. The means are there. Obviously, they are not equal. There must be some kind of separation. If you want to know the variation of the x bars, you have to find variation of x bar, variance of x bar, then square root of this one. That will give you standard deviation. So variance is sigma square upon n. Standard deviation of x bar will be sigma upon root n. So finally, for large n, when n tends to infinity, mathematically we write x bar follows a normal distribution with mean mu. This is what we verified today. And this one also quite important. We'll discuss about this in the next class. Ex bar is mu, variance of x bar is sigma square by n, and distribution of x bar is also important, that is normal. So central limit theorem talks about three things. One is mu, the mean of x bars. We have so many x bars. If you take the mean of x bar, all these x bars, that should be mu. So you can estimate mu this way. Mean of means. So many means. We have large numbers. N is very large. N should be very large. Now the second one is, it talks about variance. How the data, mean data will vary. That is sigma square by n. Not only these two, it also talks about the distribution. It follows a normal distribution. If you don't know about normal distribution, you go through the normal distribution class, but it should look like this. So this is the statement. If x1, x2, xn are independent and identically distributed random variables with finite mean and sigma square, then for large n, x bar will follow normal distribution with mean mu and variance sigma square by n. Actually, central limit theorem starts from this page. We'll have a lot. We'll discuss in the subsequent classes. If you have enjoyed the video, please like and share this video and subscribe to our channel to keep up with our latest content. Thank you. Actually, central limit theorem starts from this page. We'll have a lot. We'll discuss in the subsequent classes. If you have enjoyed the video, please like and share this video and subscribe to our channel to keep up with our latest content. Thank you.